Today we're going to put limits to use in order to understand the formal definition of a derivative. Now, we previously understood the conceptual definition of the derivative as a new function that returns the instantaneous rate of change of the original function at any point. So given a function f of x, if you want to know the instantaneous rate of change at x is equal to a, you simply compute the derivative or evaluate the derivative at x is equal to a. Now, unraveling this a little bit further, the instantaneous rate of change results in a process. We compute the average rate of change over a smaller and smaller and smaller interval until we have, in the limit, as that interval shrinks to 0, the instantaneous rate of change. So starting at the average rate of change, so suppose we have a point, x is equal to a, and we want to compute the average rate of change. So we have the average rate of change on the interval from a to a plus h. So we have a fixed point a, and then an interval between a and a plus h, where h is some constant. So we know that the average rate of change is just going to be f at the second endpoint, the right endpoint, which is a plus h, minus f at the left endpoint, which is a, divided by, so a plus h, the right endpoint, minus a, the left endpoint, which is equal to f of a plus h minus f of a over h. And the picture of this is as follows. So here's the x-axis, here's the y-axis. Now let's say I have a function like this, and then I have a point. Here's x is equal to a, and let's say that this is the point a plus h. So f of a plus h is this height right here. So that's f of a plus h, and then f at a is this height. And so f of a plus h minus f of a is this vertical distance, which is this basically the delta y, and then h is the delta x. So delta x is equal to h, is the horizontal distance. And so the delta y over the delta x gives us the slope of this line. So the average rate of change we saw is the slope of the secant line connecting this point, the point a comma f of a, to the point a plus h comma f of a plus h. So this gives us the average rate of change on this interval. Now next we said that the instantaneous rate of change of the function f at the point a is obtained by taking the average rate of change over smaller and smaller and smaller and smaller intervals. So that's why I wrote the second endpoint, instead of writing it as b, I wrote it as a plus h, because here h is going to be a parameter that we're going to allow to vary. So we're going to basically hold a as fixed and we'll treat h as almost a variable. So we'll let h go to 0. So we'll let h get smaller and smaller and smaller. Because for each value of h, I have an average rate of change. And then in the limit, as h goes to 0, I'm basically computing the average rate of change over a smaller and smaller and smaller interval, and therefore it's going to approach the instantaneous rate of change. So we can say that the instantaneous rate of change of the function f at the point x is equal to a is given by, so this is a little bit more formal definition than what we saw earlier. It's a limit as h goes to 0 of f of a plus h minus f of a over h. So let's look at some annotations here. So what we have here is an average rate of change. Right, so this is over the interval a to a plus h. So a to a plus h. That's the average rate of change over the interval a to a plus h. In other words, it's a delta y over a delta x. Right? And then in the limit, here we have a process. So we compute this average rate of change over and over again for smaller and smaller intervals. Another term used to describe this average rate of change is it's a difference quotient. Difference quotient. So, you'll sometimes see that. And the difference quotient is literally the delta y over the delta x. So the difference quotient means you have a difference of two y values and a difference of two x values, and the quotient part means that you divide the two. It's the difference of two y values divided by the difference between two x values. You could also say y2 minus y1 divided by x2 minus y1, x1. And so this is the difference quotient. It's the average rate of change. It's the slope of the secant line. The secant line is the line that, regardless of what the graph is doing, it connects the two endpoints. And it's delta y over delta x. Then when we take the limit as h goes to 0, as delta x goes to 0, because recall delta x and h are the same thing, we arrive at the instantaneous rate of change at the point x is equal to a. Now, as an extra bonus, from the way I introduced derivatives, we know that when you evaluate the derivative at x is equal to a, what you get is the instantaneous rate of change of f at x is equal to a. So therefore, f prime of a is going to equal the limit as h goes to 0 of f of a plus h minus f of a over h. So this is sometimes called the derivative at a point. The derivative at a point. And it's literally just the instantaneous rate of change of f at the point a. Now the derivative itself is a function. So we can take a step back and let a replace a with x again, because really I could evaluate this at any x value I want. It doesn't have to be x is equal to a. I can evaluate this for using a is equal to 2, a is equal to 3, a is equal to pi, a is equal to 5, anything I want. So we can rewrite this as a function, and that brings on the limit definition of the derivative. And that is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And all I did was replace that a with the x. So one thing to note is that when you're evaluating this, x is thought of as a constant. X is basically just replacing the a. So this is basically at a particular point x, f prime at x. And so when you're computing the limit, think of x as being fixed, because when you compute the limit, it's h that's changing. You're holding x down at whatever point it is. It's a variable point in the end, but for the purpose of computing the limit, x is always fixed. So x is going to be fixed, and h is this variable because you're varying the width of the interval over which you're computing the average rate of change. So then you let h march towards 0. Right? You can't actually compute this difference quotient at h is equal to 0 because you always get 0 over 0 when h is equal to 0. So you have to take the limit as h approaches 0. And then as h approaches 0, you get the instantaneous rate of change at x, which is f prime of x. So after you compute the limit, now you think of x as a variable because f prime is a function of x, and that's where x becomes a variable. Right? So you can basically get the instantaneous rate of change at any particular point by just plugging in any point for x. And so let's finish our picture that we were drawing earlier, and just do another mention that this gives you the slope of the tangent line. So let's say this is our point x, or a if you want, but we'll just call it x. So this is a fixed x value, and the tangent line looks like this. So it's the line that just touches, it's supposed to be a line, it just touches the graph tangentially. So the graph is always just slightly below that line. Now when we compute x plus h, again, it just looks exactly like the picture we had before, where f of x plus h minus f of x over h is just the slope of this line. So then, because again we have the delta y, which is f of x plus h minus f of x, and then down here we have the delta x, which is just equal to h. So as we let h go to 0, h just marches towards 0, we get values closer and closer to 0. So this would be a closer value to h, and then that difference quotient will return the slope of that secant line. And as h gets closer to 0 again, the difference quotient returns the slope of this tangent line. And as h marches closer and closer and closer and closer together, these tangent lines, like a fan, just get or these secant lines get closer and closer to the tangent line. So again, we have the slope of this secant line, smaller h gives us the slope of this secant line, smaller h the slope of this secant line, and those secant lines march closer and closer and closer to the tangent line. So this, in turn, is equals to the slope of the tangent line at x. So this is the full force, real definition of the derivative. It's the limit as h goes to 0 of f of x plus h minus f of x over h. So it's kind of like if you're driving along in your car, well, how fast are you going? Well, between 5 o'clock and 6 o'clock, if you drive 80 miles, you're going 80 miles per hour on average. So that's just this difference quotient. But then you say, well, what about between 5 o'clock and 5:01? What about between 5 o'clock and 5 o'clock and 5 seconds? What about between 5 o'clock and 5 o'clock and 1 second? Right? So as you narrow that interval of time closer and closer to just exactly 5 o'clock, you're going to get the instantaneous speed of the vehicle at exactly 5 o'clock in the limit as your endpoint moves towards 5 o'clock.